So we've done a couple of videos now about how to burn propane, and today I get to talk about a really fun topic, operational amplifiers. So we work in agriculture, margins are tight, and we build as much as we can rather than buying it. Because when we build it ourselves, we get exactly what we want. We know where the wear points are. We can replace them if needed. And then also, as I'm going to talk about today, sometimes you can spend $10 on a few electrical components instead of hundreds of dollars on a flame sensor. So I want to talk about how we use an operational amplifier to detect the presence of flame. So we want to do that because if the propane somehow burns out, like if the flame goes out, we don't want to keep pumping propane into an enclosed chamber and then cause an explosion. So very important to know if the propane flame goes out. So the basic principle is, I think I already talked a little bit in a previous video, but flame conducts electricity a little bit better than air. So conductivity of air is on the order of like 10 to the 13th ohms per meter. I think it's, it varies a lot depending on humidity, temperature, things like that, but at least on the order of that. Versus conductivity of flame is going to be on the order of 10 to the 8th or even less resistive than that. So maybe as low as 10 to the 5th ohms per meter. So given the fact that flame conducts electricity a whole lot better than air, if you can make a device that senses little microamp level changes or microvolt level changes in the current passing through the air, you can detect if there's flame present. So the way to sense tiny little variations in voltage or amperage like that is, at least I don't know if anybody else has found a better way, but an operational amplifier. So operational amplifier, obviously any amplifier amplifies a signal. So like audio amplifiers are amplifying the amplitude of sound waves. With what we're doing, we want to amplify the difference in potential across the air gap. So in our case, we have our flame rod and then we have our ground, and they're about 1/8 of an inch apart, so about 3 millimeters apart. So since that's ohms per meter, then we're talking about 3 millimeters. So we're talking about, a millimeter, of course, is 1,000th. So we're talking about, like 1/300th of that. So we're talking about like 3 times 10 to the 10th. Same here. So now we're talking about 3 times 10 to the 5th, or even less resistive than that. But like I say, that would be our ohms across that 3 millimeter air gap. So trying to detect that much of a change in resistance, and operational amplifier is a great tool for the job. So ideal operational amplifier has basically infinite amplification. So what you're doing is you're hooking up a voltage source here, and then basically you're going to ground or like a common on the other side. But bottom line, you have a voltage potential across these 2 points, and that might only be, let's just say it's 10 to the -6 volts potential difference, but still that's a detectable change. And then here you've got to feed it plus voltage and minus voltage so that it can do what it needs to do. Now, if we're saying infinite amplification, basically if there is any potential difference between, call that A and B, if there is any potential difference there and you have infinite amplification, you're always going to just run that amplification up to whatever the highest output it can generate is. So in this case, if it's a positive voltage, you would run it all the way up to whatever your positive voltage supply is. But that's not particularly useful because you're always going to have some amount of difference in voltage there. It might be nanovolts instead of the, say, microvolts that we're trying to detect, but you would always just run it up and hit your rails. So the way you end up using an operational amplifier and this is the reason it's called an operational amplifier, is you use it to conduct mathematical operations. So the way you end up using it is you always feed it back to itself. So you take the output and you either run it back to the common side or back to the input voltage side. And either operation would be useful here. But so let's just take sort of the first case where you run it back to the input side. So we take this voltage, run it back to the input. So now, and of course whenever you do this, you do need to isolate the inputs. So we put in a resistor there so that we're isolated, so that we're not back feeding all the way to whatever is supplying our voltage initially. So, but if we were to just back feed it like that, well, and then we give it a positive voltage potential, then it's going to take as much negative voltage as it needs to cancel out the positive voltage. So it'll start putting out negative voltage until it doesn't need to anymore, because there's no more potential difference to try to amplify. So, see, it's an amplifier. So if there's no signal, there's nothing to amplify. So it's going to put out as much negative voltage as needed until there's no more signal to amplify. Now, that wouldn't be useful at all, because now our output is just exactly the same as our input. You know, we're putting out just enough voltage. Well, I mean, depending on where you regard the input as being. So if this is, let's say, a 1 kilo ohm resistor, then we're going to have, you know, a tiny fraction. Like if this is our true input over here, then we're going to be putting out a tiny fraction. Now, if we wanted it to equal our true input, then we could put another 1 kilo ohm resistor there. But now that's not useful at all, because now our our output is going to be exactly the same as our input. But if we put a much higher value resistor here, so let's just say we go with a 5 kilo ohm resistor there, now it's got to put out 5 times as much negative voltage to cancel out the positive voltage. So now you've got basically 5 times amplification. Not exactly. You have to do a little bit more math to account for the fact that your input is on the wrong side of that resistor. But still, you get the idea. The other use case, of course, is you could instead of feeding back to your positive side voltage, you could you could instead feed back to your common or your ground, in which case, again, you need to isolate from the ground. And so let's just call that like a 1 kilo ohm resistor. And then, again, in order to actually amplify the signal, you need to put in another resistor here that would need to be some multiple of that resistor to ground. But you would but then instead of putting out an inverse voltage to cancel out your positive input voltage, now in order to balance out, it's going to supply positive voltage to this side until there's no potential difference and therefore nothing to amplify. So if you've got, in this scenario, if you had, you know, X voltage coming in here, and you wouldn't have the resistor in this second scenario. So you've got, let's just say you've got 1 microvolt coming in here. Well then, and then we've got a 5 kilo ohm resistor down here. So 1 microvolt coming in. So then, in order to balance it out, to make it so there's no signal left to amplify, it's going to put out enough voltage that we're also seeing 1 microvolt here. And then you can do the math on what that would work out to be. It would be something like 5 times as much voltage needed. So you would need to see something like 5 microvolts over here. So of course on a flame sensor, we're trying to take a microvolt difference in potential and amplify that up to be, let's just say, at least like 3.3 volts, enough to activate a relay or a switch, so that we can have a detection of the flame. So we need to pull in a relay with that 3.3 volts so that we know that we have flame. So instead of just a 5 times amplification, we're looking at like, so we want to sense, on the micro scale. So we're talking about like a 10 to the 8th amplification, let's just say. So we're talking about using, mega ohm resistors and, 100 ohm resistors. But still, this kind of gives you the basic principle. And then once you understand this, you can see there are all kinds of different configurations you could use. Like you could either, run a pure 5 volt to one pole, and then you could, on the other pole, start with that same pure 5 volt signal, but then measure the drop across the flame rod and ground, and use that to determine, look at the difference between the pure 5 volt and the reduced voltage, and amplify that difference. That would be one way to do it. And you can probably think of like 3-4 other ways to measure that very small dip in voltage or very small increase in amperage. But when you're talking about a difference of 100,000 times in terms of resistance, that's obviously a measurable difference, and you can use that to detect flame. So that's just sort of one example of something we've done out here. We're in farm country. We grew up in farm country, and the money's got to pay for itself. So using $10 worth of components, you can do what like Siemens, for example, wants to charge you hundreds of dollars for. That's just the kind of thing we have to do out here to make it work, and it works well. Like I say, if something goes wrong, we can very easily figure out what needs to be replaced and replace it for, say, $2 instead of $200, and that's how we're able to supply base malt at a competitive price to what you might find elsewhere.